Welcome to Physics 142 Online again. I have been getting a couple of questions about the first few homework problems on this week's assignment, and so I thought I would go over an example problem similar but not identical to those problems. If you can read my chicken scratch here on the screen, this sample problem involves a traveling wave, one-dimensional traveling wave like a wave on a string, given by the formula on the screen. Y as a function of x and t is 0.04 meters times the sine of 15 radians per meter x minus 80 radians per second t plus pi over 2. And so the first question is rather straightforward. Find the wavelength and the period of this wave. And the second, like a couple of your homework problems, asks you to plot the shape of the wave at t equals 0.5 seconds. And so that we can see the full wave, you're supposed to include at least one wavelength. So let's go ahead and do this. The fairly easy thing to do is to use the form of the wave equation and all the information it contains to find things like the amplitude, the wavelength, the period, so on and so forth. So let's do that here. For part A, we have to just remember that the wavelength is related to this quantity called the wave number k. So the wave number, not the spring constant, by the way. We use the same symbol for these two quantities. Usually they're not involved in the same problem, so hopefully there's no confusion. But k is the wave number, and it's defined to be 2 pi over the wavelength. And what we're trying to find in this part is the wavelength, so then lambda, the wavelength, is 2 pi over k. And if you remember the general form of the traveling wave equation, k is the coefficient for the x variable. And so we have 2 pi, and I'll go ahead and write down that 2 pi is of course a measure of an angle in radians. So 2 pi radians over 15 radians per meter gives us, quite nicely, the units of meters, which is what we expect, and if you work this out at 0.419 meters. So just a little over 40 centimeters for the wavelength. The period, well, the period t, the time it takes for the wave to go through one complete cycle of motion, that's related to omega, the angular frequency, as 2 pi over omega, right? And once again, we can read omega directly off of the traveling wave equation. It is the coefficient of the t variable. And so, once again, 2 pi radians divided by 80 radians per second. And the period of this wave is quite short. It's 0.0785 seconds. All right. So that's pretty straightforward. Now, part B asks us to make a plot. And let's be really clear what the question's asking for here. When we say plot the shape of the wave, all right, so shape of the wave means physically the form that you would see. So I'm getting ahead of myself here. I was going to give the answer. I'll go back and just restate it. Shape of wave at t equals whatever the value is. Here we picked 0.5 seconds. What this means is the function y of x at t equals 0.5 seconds. Right? So what I do is I plug t equals 0.5 into the wave equation up here, and then that's going to give me just y as a function of x, because the time variable will have picked a specific snapshot in time to look at the wave. And so when we plug that in, we get y of x, and I'll write in here, just to make sure you understand what I'm doing, t equals 0.5 seconds. So y of x at t equals 0.5 seconds is easy to write down. 0.04 meters is the amplitude. We have the sine of, and I'll skip the units because you can see them up on top, 15x. If we plug in t equals 0.5, half of 80 is 40, so it's minus 40 in units of radians, right? Because time in seconds multiplies radians per second to give radians. And then we have plus pi over 2. Pi over 2 being this phase constant that was in the wave function to start with. So this, what we have left, is simply a function of x. So we really want to then plot, we want to make a plot of y versus x at this particular time t. And the problem doesn't say so, but let's assume that x doesn't go negative. In other words, the rope or the string begins at position x equals 0. And in this case, it is, because of the minus sign, traveling to the right. So we'll just use positive values of x. But how do I make this plot? Well, the easy way to do it is to make a little table, or the straightforward way to do it is make a table where you plug in different x values and then evaluate from this equation the y values and then make a plot. Okay, we can do it that way. Or if we want a nicer looking plot and want to do less punching in numbers on a calculator, we can throw this on a spreadsheet. So I'll do a little bit of both. Because I'm not too confident about my freehand abilities with plotting, I will make the table and then I'll show you how to do it in Excel if you want to make a nicer looking graph. Of course, you're free to do it either way you want as long as you hand in your work. So the table here, if we make a table for x values in meters and then the corresponding y values in meters, a couple things we have to do though to make this table work well is we have to figure out what x values we want to use, right? Can I start at 0? Of course, that'll be the first point. And should my next point be 1 meter, 2 meter, 3 meter? Or do I need to use points in between? And how many points do I need to use? Well, we can get a clue by looking at the value of the wavelength. That's why it was a good idea to calculate the wavelength first. So the wavelength is about 0.4 meters. So if we're going to start at x equals 0, we've got to go through to at least 0.418 meters, or 0.419 meters. And let's go all the way to 0.5 meters, just so that we can make sure we capture a complete wavelength. Well, let's see, how many points do we need in between 0 and 0.5? We better give enough so that we can see the shape of the wave. If we just pick 2 or 3 points in that region, we might never see evidence for a wave shape at all. So my proposal is to divide it into 10 equal intervals. So we'll go 0.05, 0.1, 0.15, 0.2, 0.25, and so on, like that, all the way down to 0.5. I think I can sneak in an extra point here at the bottom of the screen, at the risk of losing the top of the screen, but this is good enough. All right, and I'll just plug in the values, right? We plug in x equals 0, so we're going to end up with 0.04 meters times the sine of negative 40 plus pi over 2, and that works out to be negative 0.027. Negative 0.027, of course, in meters. Now, the thing you have to be careful about, remember the argument of the sine function in this kind of equation is in radians. So make sure, if you're punching that out by hand, that your calculator is set to evaluate the sine of a radian angle. 0.05 gives something very close to 0. It's 0.0008 meters. 0.1 gives 0.028, which is about the same positive value as x equals 0 gave a negative value. So those two are pretty symmetrical. The next one gives almost exactly the maximum displacement. Because remember, the amplitude is 0.04. This gives 0.0399. So x equals 0.5 just about happens to be the right value to give the maximum displacement. 0.2, then we should expect that this would come down. 0.031. 0.25 gives 0.0049. Then it becomes negative, right? Because as we see, as x increases, for a while the y value is increasing, and now it's decreasing again, and eventually it's going to cross 0 and become negative. And so this is negative 0.024. 0.35, negative 0.039. 0.4 gives negative 0.034. 0.45, negative 0.010, and by the time we get to 0.5 it becomes positive again, 0.019. So one can take those values obtained by plugging in different values of x and plot them on the graph in order to generate the shape of the wave at this particular time. If we picked a later time, a different time besides 0.5 seconds, we would get a different shape, just telling us that the wave travels. Right? The shape of this wave changes with time, reflecting the way that the peaks and the troughs travel, in this case, in the positive x direction. Okay, but I'm not going to take the time to do that here because it won't look very pretty. So instead, I'm going to pause and come back in a second with a window from Microsoft Excel to show you how to do this relatively easily and in a way that looks much nicer. All right, well, here is an Excel spreadsheet where I've just typed in as text the wave function y of x and t in exactly the same form that I had on the screen a few minutes ago, except I've just written in pi/2 for pi over 2. So the assignment is, with that general shape or that general form for the wave function, let's plot the shape y of x at t equals 0.5. So I showed this already, but if we plug in t equals 0.5, then we get 0.04 meters times the sine of 15x minus 40 plus pi over 2. And so we decided with x that we were going to start with 0, of course 0.0, and then increase it in increments of 0.05. So I'm going to type in a formula where I add 0.05 to the previous cell to generate the x values. Then with that formula in the cell, I can copy it down and paste it in order to get down to 0.5. So I don't have to type those numbers in. I can just generate discrete values from the formula. Now for y, I just have to type in the equation carefully, 0.04, right, times the sine, and the sine in Excel by default wants an angle in radians. So that's good for us here because I'm going to take 15 times, and the value that I want to multiply by is the value of x. So since I'm going to copy this formula down in just a minute, let me put in the cell value. Rather than type in the numerical value, let's type in the cell value. All right. So that's kx, 15x, minus 80, 80 times t. Okay, we know what that is. That's just 40, minus 40, plus, and now here's the weird thing. Rather than type in a numerical value for pi, I'm going to use the functional value, the built-in function in Excel, which is at pi, and then you have to put the left and right parentheses in. At least in my version of Excel, you have to do that, divided by 2. And so that formula should, if I did it correctly, it should give me the value negative 0.027. Good. All right, and we've got that. So all I have to do to generate the other values is copy that formula into the cells below. And we see, once again, that the wave goes through a peak somewhere around here where the y value is largest, and then it decreases and becomes negative, again reaching a rather large negative value, and then crossing 0 finally by the last point. And so an easy way to do this graph, if you just have two columns of numbers and you want to graph them, is just highlight them, do insert a scatter chart, only we'll connect it with lines here, and we get a very nice simple plot of the wave function at this time. So what we see again is that it's not, it is a sine wave, of course. It doesn't begin though at x equals 0, y equals 0. It's shifted over a little bit because, first of all, there is this phase constant, pi over 2, and plus, we're not looking at the wave at t equals 0. We're looking at some general time, t equals 0.5 seconds. Okay, so it's not a pure sine wave, and we shouldn't expect it to be. Only at very special times will it look exactly like a sine wave that begins at the origin. And so that's all there really is to it. You can certainly finish this off by hand, but it only takes a couple of seconds to generate a plot like this from Excel, properly labeled, then if you hand in the whole thing, print this whole thing out, then that would be a nice way of generating solutions to the homework. Of course, what you turn in has to reflect your own work, and so if a friend does it, you can't just take a copy of the friend sheet. In any case, I hope that this is helpful in reviewing all of the information that's contained in the traveling wave function. It's really very full of information. So just to recap then, if we look at this sine 15x minus 80t plus pi over 2, 15 is the wave number. 2 pi divided by the wave number gives us the wavelength. 80 is the angular frequency omega, and 2 pi over omega gives us the period. And so those are the quantities we calculated. Of course, the coefficient out in front of the sine function is the amplitude, and this gives us lots of information about the way the wave propagates and the shape of the wave, its wavelength, its frequency. And one more time, we could get the wave velocity directly from the wave function here, because we know that v, the wave velocity, is equal to omega divided by k. And so in this case, if we wanted to go one more step further, we could solve for v as 80 over 15. And because of the units, that would be in meters per second. I hope this is helpful as you're finishing up your homework problems, and I'll see you in class.